Hi everyone, today we will discuss the concept of curvature of a curve, sometimes called absolute curvature. If we have a smooth regular curve parameterized on the interval AB, then its curvature will be a function from AB to the non-negative real numbers. This function will measure in some sense how different is our curve to a straight line. Notice that if we move along a straight line, even though the speed can change, the direction remains constant. The curvature is defined as how much the direction changes as we move along the curve. In order to define it, we need the tangent vector corresponding to the velocity. Remember that if gamma is smooth, its derivative is a vector that points in the direction in which the particle is moving, and its length corresponds to how fast is the particle moving. Since we only care about direction and not the speed, we normalize gamma prime to construct the vector uppercase T, also known as the tangent indicatrix of the curve gamma. This vector t always points in the direction in which the particle is moving regardless of the speed, well, provided it's not zero. That's why we ask the curve to be regular. We don't want to divide over zero. With this, the curvature at time t is defined as the norm of the derivative of uppercase t divided by the speed at the corresponding time. The numerator contains the exact piece of information that we were looking for. How much is the direction changing? What is slightly more mysterious is the denominator, but it turns out that it is just a term to make this quantity invariant of the parametrization. This can be shown by applying a couple of times the chain rule we discussed at the beginning of lesson 3, so I leave it to you. Also, by expanding the definition of t in terms of the velocity and the speed, one could compute the curvature with a direct formula. Finally, I want you to notice that in the particular case when we are working with an arc length parametrization, uppercase t and gamma prime coincide, and the curvature is simply the norm of the second derivative of gamma. When we integrate the curvature, we obtain what is known as the total curvature. To make the integral invariant of the parametrization, we must multiply the integrand by the velocity. The total curvature is defined even when the curve gamma is only piecewise smooth regular. This is done by adding the total curvatures of all the smooth pieces and adding the change of directions at all the breakpoints. In the case the curve gamma is closed, the total curvature is defined slightly differently to include the net change of direction, that is, the angle between the initial velocity and the final velocity. Now, to gain more intuition on the total curvature of gamma, you can prove this formula. This is straightforward as you only need to write carefully the definition of phi, and remember that for a C1 curve, its length is the integral of its speed. What is really cool about this formula is that it also holds for piecewise smooth regular curves. Let me show you what I mean with some pictures. We will analyze some curves on the left, their tangent indicatrix in the middle, and follow the tip of the tangent indicatrix as the trajectory of a particle on the right. These pictures are two-dimensional, but the concepts we illustrate here work equally well in 3D. The most simple example is a straight line. Here t is constant and the total curvature is 0. For something that is not straight anymore, the total curvature is obtained as how much the tangent indicatrix changes. We illustrate that here as the pink angular segment on the right. For example, for a circle, its total curvature is 2 pi as the tangent indicatrix makes a full trip around the unit circle. Now, for something that is piecewise smooth regular, we can think of the changes of direction at the breakpoints as t making a shift from one position to another, and the total curvature is still interpreted as this total distance traveled by the tip of the tangent indicatrix. Now for closed curves, as we mentioned before, we also consider for the total curvature the change of angle from the final direction to the initial direction, corresponding to that last angular portion required to fill the cycle. And one interesting problem we can solve together is the following. Imagine we have a closed curve inside a round region of radius 1. Then its total curvature is at least its length. We will prove it today for piecewise linear curves and leave for later the general case of piecewise smooth curves. We will begin by considering the triangles formed by taking one segment of the curve together with two segments going to the center of the circle, and putting all those triangles together along a straight line. Since we were just moving things around, the line segment that goes from left to right has the same length as our initial curve. Now we put one more copy of the first triangle in our line and draw the piecewise linear curve that goes along the tips of the triangles constructed. By the triangle inequality, this yellow curve will be at least as long as the blue segment, so we are left to check that its length is bounded above by the total curvature. Comparing the exterior angles of the curve gamma with the angles in our configuration above, we see that either they are the same, like for θ1 and θ2, or they are wider in the curve than in the configuration above, like for θ3 and θ4. Also remember that the non-horizontal sides of these triangles were shorter than 1, because they are segments from the interior of the circle to the center. By the law of sines, this means that the first segment of the yellow curve is at most θ1', the second is at most θ2', and so on. Summing over all of these segments, we see that the total curvature, which is the sum of all θ's, is at least the sum of all θ', which is greater than the length of the yellow curve. Finally, the yellow curve is longer than our initial curve, finishing the problem for piecewise linear curves. And that's it for today. Keep learning, having fun, and see you next time.